Oh God, I get paid for doing this. Would you believe this? They're actually giving me money. Okay, let's get started. News section, the last of the last. Applications. So first thing we're going to look at are what are called Taylor's polynomials. So for any function y equals f of x, its Taylor polynomials, because there's more than one of them, is given by this formula. Tn of x, so n's going to be a number, so you're going to be asked to find t3 of x, t5 of x, t2 of x, is given by this. Do you notice it's just a piece of Taylor series? Technically speaking, although you're never asked to do this, isn't f of x, technically speaking, t infinity of x? Right. We know that it's very, very difficult to get general formulas, right? We tried some yesterday, I think. Did we do the cosine or the sine? That's usually one of those two is one I pick, right? Was it cosine? And wasn't it really messy and really ugly and hard to keep track of? And that was for a simple function. Many, many functions, finding this general formula is downright impossible, practically speaking. But we have a kind of safety thing. Taylor's polynomials will approximate the real function. So if I found t5 of x, it might not be exactly the same value as f of x, but won't it be dead close? So if you can imagine this is f of x, if you did t5 of x, wouldn't it probably look something like this? It's pretty good for at least a fair chunk of time, right? And if you're only interested in being pretty good and not being perfect, can't Taylor's polynomials do the job? Can't you just find a t3 or a t5 or a t7? And would it also be fair to say the bigger the n, right, the bigger this guy is, the closer to f of x the function gets? Would you agree that a t10 of x is a better approximation than a t2 of x? So let's put that into practice. I'm going to pick a very simple function, f of x, sine x, and we are going to center it at 0. And let's find some Taylor polynomials. I'm going to find t0 of x, t1 of x, t2 of x, t3 of x. Now that should be enough. t0 of x is actually just the value of the function, right? That's 0. And it's a sine of 0 equals 0. So that's pretty useless one. t1 of x then is going to be f of 0 plus f dashed of 0 x over 1 factorial. And I just realized I have to do something here. I apologize. We need to know what all these derivative guys are, so I'll write them over here. Okay, now we also need to know what the values of these derivatives are at 0. And that's 0, this is 1, this is 0, and this is 1. Okay, so now that I've got that guy set up, I'll do my guy a little bit clearer. So I'm just repeating myself. This is the question, just so it's all in the same piece of paper. So to find t0 of x, that's just the value of the function at 0, and that's 0. you want to find T1 of X, it's f of 0 plus f dashed of 0 x over 1 factorial. That's 0 plus, well, I'll put it all in. That's x. So that's T1 of X. T0 of X is not very interesting. If you do T2 of X, it's this fella plus that guy. Plus that guy. Unfortunately, these two guys are 0, and the only guy that you've got is this fella here. So have you noticed that those two guys are actually the same polynomial? And the reason that happened was that this term here didn't add anything to it. So there's one last one that we're going to get, and that's T3 of X. And that's f of 0 plus f dashed of 0 x over 1 factorial. Have you noticed that the way these things work, can't you just use the previous answer and then just add one more term? So if you're thinking about cutting down on your workload, isn't T3 of X the same thing as T2 of X, which is what all of that is, plus this fella? Does that make sense to you, that you can just reduce your workload a little bit? Because T3 of X is all the guys that made up T2 plus one more term, and the one more term is this last one. And this guy is 1, this is x cubed, and this is 3 factorial. So what do you get? You get x, and I have a -1 here. Yeah, and negative x cubed over 6. So we now have all the different Taylor series up to T3 of X, Taylor polynomial, sorry, T1, 2, and 3 for sine X. That is interesting. So I am going to test it. Here is T2 of X. It's approximately that guy. I wonder how good it is. Give me a small number. That means give me an x between 0 and 0.2. Just randomly give me a couple of decimal places between 0 and 0.2, and we'll check it out. Come on, give me a decimal.
0.1.
Oh, come on, stick another digit on it.
0.15.
Stick another digit on it.
0.15672.
There, right? Let's test that one. Now, according to Taylor's, shouldn't the sine of 0.15672 be roughly x? Oh, it should be roughly equal to 0.15672. Let's find out. First thing I'll do is make sure I'm in radians, which I am. And I am going to do the sine of 0.11672. Okay. Do you think it's going to be close? Do you think it's good to at least 1 decimal places, or 2 or 3 or 4? How accurate do you think this is going to be? Do you think we'll be lucky if we get the 0.1 bit right? What do you think? Gut feeling.
About 3.
Okay, let's see what it is. It's 0.156079. I'll write underneath it 0.1562. Okay, I'll make that an 8 then. Whoa. Oh, come on, that should be impressive. That the sine of x isn't that good to most of the third decimal place, like Victoria said. So if you lost your calculator one day and you needed to find the sine of 0.13 radians, wouldn't the answer be dead close to 0.13? Well, let's try T3 of x. Well, T3 of x is x take away 1/6 cubed. So shouldn't that be a little bit better, right? A little bit more accurate. So let's find what the approximate value is. So it's going to be 0.15672 take away 1/6 of 0.15672 cubed. Okay, that one was good to 3. What do you think T3 is going to do? Going to be better, isn't it? You get any gut feelings? Well, here we go then. 0.156078465. That's what my calculator told me. And I'll put in the sign again because I lost that one. 0.15672. And the sign of that guy is 0.15607.9. If you're an engineer, would you be pretty happy with using that guy to approximate the sine of x? At least as long as x is pretty small, right? Well, you're smiling. Is that amazing to you that it's that good?
Yes, I am utterly astounded and my worldview has been shattered.
Oh, man. I did a good job today to shatter someone's worldview.
Do you think this is pretty cool? Because you could also use this to find the integral of the derivative of something that you normally couldn't, like if you want to find a definite integral of something.
Yeah. So if you wanted to find the approximate value of an integral, couldn't you plug in a T5 of x, which is just a polynomial, integrate it, plug in the start and finish number, and couldn't you get an answer good to 6 decimal places? Engineers as happy as anything, right? You only
It's a
needed
lot better
3.
than like Simpson's rule.
Oh yeah, Simpsons a little bit messier. So I don't know this for sure because I don't have an insight into the TI-84, but I wouldn't be surprised if the way the TI does its job, right? For how does it know what the right value of sine x is? It's probably got a Taylor's polynomial formula for sine x. And when you do sine x, it basically just does a big polynomial. You know, maybe it does a T10 or something, right? And boom, perfect. I want to show you what's going on in Desmos. So if you can hang in here for a little while, I need to find Desmos because I didn't set it up. Okay, I'm shrinking this down, hopefully to a size I can see it. That looks good.
So is this a way to more accurately find the value of pi versus just measuring like a circle and comparing? Because I've heard like a lot of different methods on how people propose we solve for a value of pi, a numerical value. But would this be a better method?
Well, it'd be better than some. You find a function whose answer is pi or a multiple of pi, like half pi, I'd probably do something like inverse sine of x, right? I do a Taylor's polynomial for inverse sine of x, right? Something like that. Maybe do it to T10, and then you could just plug in whatever it would be, 1 probably. You know, the inverse sine of 1 isn't that pi, you know, or it's actually half a pi, but you know, you can double the answer. You could do it that way. I think they have much more brute force methods, because what they do today is they just give a computer a very stupid way of doing it, but it can do it like to 1 billion calculations a microsecond. So it gets a really accurate answer because of that. Right, I think I'm ready for this. This is Desmos. So here goes. Y equals, I think I've overdone the size. There. Y equals, let's see, you can do sine of this, can't you? And the minute you do brackets, it recognizes it. Okay. So we're all happy with sine x. Let's just zoom it in a little bit more, right? Here's sine x. And T2 of x was just x, wasn't it? Now, can you see that it behaves quite linearly? If I zoom in for a minute, would you agree that the sine x and y equals x are almost identical for what, about 0.3 to negative 0.3? You see how good that fit is? Now, if I take that guy and we put in our T3, which is a little bit messier, it's y equals x, and then you take away 1/6x cubed, so I'll have to set up a fraction here. Can I do that? No, you only need to do it as like that. Yeah, good. An x cubed. Now, if you add that guy in, if I kind of zoom out a little bit, do you see how the straight line doesn't really work? Can you see that the green one at least is beginning to curve a little bit more? Secondly, if we zoom on this side, isn't the green one following the original function a lot further before it starts drifting? Now, if I take this guy, and you just have to trust me in this because I've memorized the same function, and I go to the next term, let me make sure I get this. That's 3, 4, 5 factorial. Why I needed brackets in. Did I put those brackets in myself? I did. Okay. Plus 120 x to the power of 5. And what's that? Purple. Whoa. Can you see that the purple follows even better than the green? Now, eventually, doesn't everybody drift? But if you do t to the 20, which I'm not going to do, can you trust me if you do t to the 20, it does a couple of cycles before it drifts? And t to 1,000,000 would go a really, really long way before it drifts. So, have we convinced you that these Taylor polynomials do a good job of being similar to sine x? And the bigger the t polynomial you use, right, the Taylor series polynomials that you use, the more accurate you get your answer. I think that's quite impressive. I like it. Okay, back to doing some questions then. So the one I just did was actually virtually question 1. And they have a whole load of pictures which you can check out in your own time. Now, here is, the next question. And this kind of shows you why you need to do Taylor polynomials. You suppose you were given this function. And we are going to only find T3 of X. And trust me, that is going to be a lot of work, right? So the question was find T3 of X, the Taylor 3 guy. If you try to do this fella and generalize his formula, right, try and find this, can you trust me it would be downright impossible, practically speaking. But we can still find T3 of X because that we can do that because we're only going to differentiate a few times. I'm 99% sure that this is a damped oscillation question. You know the guys that go like this, one of those guys? I'm pretty sure that's what this function is. So here we go. T0 of X is f of 0. In this case, it's 0. I need to find the first derivative. And then I need to find the second derivative. And then finally, I need to find the third derivative. And I'm already regretting this question, but since I've started it, we'll have to finish it. Would you agree this is a product rule? So it's going to be f dash g plus f of g dashed. It is going to be the derivative of this guy, which isn't just e to the negative 3x. What's the complete derivative? What have I missed?
-3.
Yeah, because it's a chain rule thing, right? Followed by the sine of 2x plus leave this guy alone and differentiate the sine of 2x is the cosine of 2x. And what else have I missed this time? The sine of 2x isn't just the cosine of 2x.
2 cosine.
Yeah. So I'm going to pull those guys together and have -3 sine of 2x plus 2 cosines of 2x. And that's f dashed of x. And so f dashed of 0 is basically 1, nothing, and 2. So all that hard work was just to find out that that guy was 2. Okay, I'm going to cheat here. Can I pretend they wanted T2 of X? Right, just saves us one more. So all I'm going to do now is one more derivative, which is this ugly guy. And I'll call this F, and I'll call this whole mass here G. And so you differentiate this guy, it's a product rule. And this guy is e to the negative 3x times -3, and you leave the other guy alone. Plus, you leave the first guy alone, and then you differentiate these two. If you differentiate this guy, you get -6 cosine of 2x. If you differentiate this guy, you get -4 the sine of 2x. And then you find the second derivative at 0. This guy is 1. That's nothing, and that's 2. This guy is 1. That's -6, and that's 0. So hopefully I've done this correct, and you got -4. So T2 of x is f of 0, f dashed of 0, x over 1 factorial, second derivative of 0, x squared over 2 factorial. This guy is 0, this guy is 2, and this guy is -4. That guy gets you 2x, and this guy gets you 2x squared. Can you see how much work is involved in just finding T2 of X? Can you pretend that that's what was asked? If you were being asked to find T3 of X, wouldn't you have to take this horrible mess and differentiate it one more time? Now, what you would do next, which I'm not going to, is can you plug that into Desmos? Then plug that guy into Desmos. And with a bit of luck, wouldn't you see that they sort of have fitted round about zero, right? They'd be pretty close at zero, and then they would drift a reasonable amount away.
So what if I wanted to find a value of a function at like a specific point, like x equals 3? Could I do this whole thing except take the derivative at x equals 3?
If you wanted to find the value of this function at 3, you just replace the x here by 3.
But you're saying it only does a good approximation around f equals 0.
Oh yeah, if you want to do one at x equals 3, you just do a Taylor's polynomial, but you center it at a. So this would become x minus 3. This would be the various derivatives at 3, and that would still stay as k factorial. They actually do that in later questions, so you'll get to see it happen. Because what you don't want to have to do, imagine, let's be silly, imagine you wanted to do a function, but you were only interested in values of x around about 100. If you did a Taylor's polynomial centered at 0, wouldn't you probably need thousands of terms to be good at that far out place, right? At x is x is 100. Wouldn't it be much easier if you just shifted your center to somewhere like 99 or something that's dead close to the place you're interested, and use that instead? And that formula allows us to do that. I have this guy set up. I'm not going to do it, but couldn't you use this to estimate the value of the original function at 0.1, 0.4, something like that? And it would be pretty good. Check my time. Let's see. Oh, good. This is a version of question 4. And this does a little bit more than what we've done so far. Here is our function secant x, not very pretty, centered at 0. That's good. And they say n equals 2. That's just another way of saying, find him. And they got this little bit at the end here, which we won't worry about until later. But we are going to find T2 of x centered at 0 for this function, and we're going to use it in this range. So let's set the ball rolling. Right, the value of the function at 0 is the secant of 0, and I hope you all know that's 1. Since we're only going to go as far as T2, that's good news, because it means I don't need to differentiate too much. The bad news is that we have to differentiate things you probably haven't done for a while. What is the derivative of secant x?
Is it secant pan?
It is, well done. And if you do f dashed of 0, and you find secant of 0, tan of 0, what you get is 1 times 0. Oh, it's 0. So that means that middle term, the x term, isn't going to exist. Now to finish, I need to do the derivative of this guy. So I'm going to call this f, I'm going to call this g, and I'm going to do our product rule. Oops. F dash g plus f of d dashed. If you differentiate a secant, you get a secant tan. Leave the original function g alone, which means it's another tan, so I'll just put a tan squared there to save time. Then you leave this guy alone. And what do you get if you differentiate tan x?
Secant times tangent.
That's what you get when
Oh.
you differentiate a secant.
Ah.
but you were
This is
close.
secant squared.
It's a secant
Okay.
squared. So can I call that secant cubed to save a line? So we now have our second derivative, and we're going to evaluate our second derivative at 0. And it's going to be secant 0 tan squared of 0 plus secant cubed of 0. So it's 1 times nothing squared plus 1 cubed. Well, that's just nothing, and that's 1. So we got 1. So the guys that we are interested in are these numbers. The second derivative at 0, the first derivative at 0, and the original function. So to get t2 of x, it's f of 0 plus the derivative at 0, x over 1 factorial, plus the second derivative of 0, x squared over 2 factorial, right? That's the general formula for all t2 of x's. This is 1, this is nothing, and this is 1 times x squared over 2. So it looks like we have that guy. We have found t2 of x. Are we good? Are we comfortable? Well, as long as I haven't screwed up, which I have been known to do, are we comfortable how we found t2 of x for the secant function? So what I'm going to do now is use Desmos and see how good a fit it is. Because what this will do is it will allow me to tell if I have screwed up. Shouldn't it be a reasonable approximation to secant x, at least in this small range, right? So nip over here and switch it so you can see me do it. And let's see what we get. The original function is, come on, secant. If I put a bracket, will it accept it? Yes, it is good. So it likes secant x, that's good news. There we go. You remember from trig, secant? Get that out of the way. Ooh, that function is going to have a problem. Would you agree it's got vertical asymptotes, which polynomials don't like, which is probably why they restricted it to the range they did. So it's 1 plus 1/2 x squared, which is this guy. Now, that's the red guy. So I'm going to zoom in. Now, they're only interested in negative 0.2, which is here, right, to positive 0.2 is here. Do you see this is a pretty good fit already, isn't it? You see the black and the red almost on top of each other. Now, I'm going to lose it a little bit because when I zoom in, you won't be able to see the x-axis. But remember, each one of these lines is 0.1. There we are. Okay. This guy here is 0.2, so I'll try and keep my focus on that. Oh, come on. Is that not a pretty accurate fit? I mean, for any engineer, wouldn't you be quite happy to use that quadratic for the secant function, as long as it's not, you know, miles away, right? 0.2, negative 0.2. Who knows? I wouldn't even want to guess. It could be, what, 6 decimal places good? Definitely very accurate. And let's leave that and talk about the new thing in town. We have a new guy called the remainder function. I'm going to try and show you in a few seconds once I get back
Wait,
to my
so
whiteboard.
Can I ask a question? What's
Sure.
the point of having the range, like of the negative 0.2 to 0.2? Is that just like to check your work?
The range is there to make it a well-behaved function. Remember, there was horrible vertical asymptotes on this function. So they chose 0.2. They couldn't have chosen 0.5 and minus 0.5 and it would have been okay. So the range, one of the reasons they had this range is to keep nice things, right? To have a nice curve in that range, right? But they have another reason for why they're picking it, is because if you only use values in this range, isn't it going to be really accurate? And so it allows you to say, as long as you stick in this range, you're going to be really accurate. To which someone should ask the question, how accurate do you mean by really accurate? In other words, how good is this guy to being secant x if you only use numbers in this range? And that's where this fella comes in. It's the remainder, or is it sometimes called the error function? And it's typically called Rn of x, because the remainder function depends on which Taylor polynomial you're going to get. So if you were saying, well, what is the error? Isn't the error the difference between the real value and the Taylor polynomial? Would you agree? But they stick absolute values around it because we don't really care if it's 0.1 too big or 0.1 too small, right? We don't need to worry about plus and minuses. So this guy here is the remainder function. And what that tells us is, if I can find the maximum value of that remainder function for x's between, I don't know, let's say 0.2 and negative 0.2, can't I then say to people, you can use this guy to be secant x, and your answer is good to 10 decimal places or 1 decimal place. And this remainder function is the guy that's going to tell us how good this guy is to being that guy in any given range. So you're going to have to be told this range. Okay, so how are we going to come up with this number, right? Now, I know who this fella is. He's secant x. And I know who this fella is if I'm doing, right, let's do the remainder function on this situation, right? So this guy is going to be t2 of x, so that's going to be 1 plus a half x squared. And that's going to be secant x, take away a 1, take away a half x squared. And aren't we interested in the maximum value of this guy? Right, what's the biggest difference between the real answer and the approximate in this range? Now, there are two different ways in which we are going to come up with this error, right? The remainder function, right? It's going to be a number. The biggest value for this guy. The first one is we're going to use essentially Desmos and calculations. And the other method, which we won't get to today, is going to be purely algebraic. So let's do the first one. If you plug this guy into Desmos, weren't the two guys almost on top of each other, right? If you looked and zoomed in, can you trust me that eventually what happens is that it drifts? Would that seem reasonable? Also, wouldn't the biggest drift be at the endpoints? In other words, you're going to have the most error the furthest away from zero you get. Would the logic of that seem reasonable? Right. So all you need to do in the number crunching version is find out what this is equal to when x is 0.2. I guess I should check the other side as well in case one of them's got more error than the other, and that should do it. So if you find the value of the remainder function at 0.2, and then you find the value of the remainder function at negative 0.2, and whatever one of these is the biggest, isn't that the worst case scenario? You'll never do worse than that. So we are going to find the secant of 0.2, take away 1, take away a half of 0.2 squared. And in this case, we're going to find the secant of negative 0.2, take away 1, take away a half, negative 0.2 squared. My calculator doesn't have secant, but 1 over cosine will do the job. So it's 1 divided by the cosine of 0.2, take away 1, take away a half times 0.2 squared. And the answer I got is that fella. So it's roughly 3.4 times 10 to the negative 4, which means it's 0.00034. Very, very roughly, would you agree that it's good to 3 decimal places? So if you want to use this quadratic to represent the secant function, and you only do numbers in the range +2 to negative 0.2, whatever the polynomial gives you, it's going to be good to 3 decimal places with the real answer. So don't we now know we have a number for how accurate it is? Does that make sense? Can you trust me if I did the other one, you get a number very similar to that, probably actually identical. Are we good? That means that can't we do every calculation we ever wanted to do to 3 decimal places and do them all with polynomials? And that is a perfect time to finish. So last name and bye-bye. I'll see you tomorrow where we'll continue working with these guys.